some ideas concerning the second midterm exam. First question was involving buffers, how to make them, and to do some calculations. So when I'm seeing this question involving buffers, I see a target pH, an acidic buffer, pH of 4.25. I'm thinking about how the acetic acid would be a good choice to have involved within that buffer. If I look at a titration curve involving a weak acid like that, I have a buffer region. At that buffer region, I have a combination of both the weak acid and its conjugate. Both of those in the beaker at the same time, that's what I have within this buffer region. Henderson-Hasselbalch equation is a good way to think about the relative amounts of the acid and the base form of the buffer there. Finally, the pKa for acetic acid is about 4.7. So if I'm thinking about what I could use to make a buffer in the acidic region, I need to have a weak acid and its conjugate in the beaker at the same time. So I could take different solutions. I could take the acetic acid and add a solution that included its salt. That would put both in the beaker at the same time. I could start with the acid, add some base, and convert it. So that way I'd have both the acid and the conjugate in the beaker at the same time. Or I could start with the conjugate and I could add some add some strong acid and bring that back to get both in the beaker at the same time. So I need to be in this buffer region. I can either add the two components or I could convert the acid to the conjugate or the conjugate back to the acid by adding sodium hydroxide or HCl. Those would be the different ways I could make the buffer. If we have a target pH of 4.25, you could plug in the pKa value. You know what the pH is, and you can solve for then the ratio that you need involving the concentration of the base form and the acid form. So that ratio is around 0.32, so I could mix together solutions that would lead to that ratio involving the concentration. Finally, in terms of the activity, I'm thinking about how ions can cluster together, and the activity would then be diminishing their amount relative to what their concentration had been. H+, that's an ion that could be involved in the clustering, and if the H+ is diminished, there's less H+ present, so the pH is going to increase. This one's involving a titration. I see HF, which is a weak acid with a Ka value listed, and I'm titrating it with calcium hydroxide, which would be a strong base. So I'm thinking for the initial pH, I'd be using an ice table. When I'm thinking about the volume to reach the stoichiometric point, I need to have a balanced reaction. And then at the stoichiometric point, I'm thinking how the moles of the HF have been converted over to moles of the fluoride ion. And with that fluoride ion, I could then put that into an ice table where it's going to act as a weak base and use a Kb value. Here's some shown work. So this is setting up an ice table, working it through to get a H+ value, pH around 1.9. Here's a description to get the volume of base needed to get to the stoichiometric point. This is accounting for a factor of 2 to 1 when we're looking at the aspect that I have 2 moles of HF for every 1 mole of calcium hydroxide. pH at the stoichiometric point, there's a lot of features to this one. Here's some shown work. So the first step would be to recognize that all of the HF has been converted over to the fluoride ion. I have the number of moles of that and then the total volume because I want to use the concentration then in my resulting ice table. I need a K value for that. A Ka was given for the acid, so I'll convert that, or the student will convert it over to the Kb here. Set that through, neglect X within our analysis, solve for X along the way, which is going to be the hydroxide, POH to pH for this. This one we have a metal hydroxide, and we're going to, first of all, consider what would it mean if we adjust the pH to 10 on this? How would that affect the molar solubility? So to answer it, we could use a KSP value to determine the initial hydroxide concentration that would be in the beaker, and from that, see what does it mean to adjust it to 10. By using the KSP value, we can solve for what the molar solubility would be. And we could also, within this, I'd say more important than the molar solubility, we can solve for what the hydroxide concentration is. By using the hydroxide concentration, we could calculate the pOH and then the resulting pH. So we first want to consider what would be the amount of hydroxide there if it was a saturated solution, because that's what corresponds to the molar solubility. And then consider what would it mean if we adjust it to 10. By adjusting it to 10, we're adding some acid in this case to remove some of the hydroxide from the solution, and it's described here with Le Chatelier. That's going to shift the equilibrium, and it's going to increase the molar solubility. Looking at this particular titration curve, identifying the buffer regions, that would be my plateaus B and D. Most people did a really good job with that. I like this student's work where they're showing what was the in the beaker at each of the different regions. And we see that along our buffer region, we have a combination of our weak acid and its conjugate. And in this region, it would be the subsequent weak acid HA minus all the way to the base of the A2 minus. That's what we'd have along each of the different regions for B and D where we have our buffers present. Now, this idea of comparing the strength of H2A as an acid with the base A2 minus, when I was asking here, support your answer, people looked at the different titration curves and took away different information. One thing that people commented on was the length of the buffer regions. Buffer region B versus buffer region D. That actually isn't dependent on the strength. That depends on how close together the Ka values are. Closer together, the more they end up getting merged, and you don't have as long of a plateau. That's what that feature is describing. If I look within this, though, if I'm thinking about my Henderson-Hasselbalch equation, I have the case where halfway through my particular buffer region, my pH is equal to my pKa value. That would be true for buffer region B and for buffer region D. So if I were to estimate within here, I could get a sense for what would be the pKa, a little bit over 2 when I'm thinking of that in terms of the acid H2A. And I don't know, maybe about 7 when I'm looking for the acid HA minus. I could also think about those in terms of their corresponding pKb values when I'm coming back in the opposite direction and I'm thinking about the species behaving as a base. So my comparison ends up being, tell me about the pKa for the acid H2A. Tell me about the pKb when I'm thinking about the A2 minus as a base. This student's description, that's what they're going after. They're doing that same kind of analysis to get a sense of what the pKa values would be, and then thinking about it as far as the strength of the H2A as an acid, and thinking about the strength of the A2 minus as a base. We're looking at this one. We've got a lot of different scenarios, so we're looking at different ways that you can influence the molar solubility. So key initial thought here, we have a saturated solution, and we're thinking about the molar solubility. So if I'm thinking about a saturated solution, I have like a KSP expression. If I'm envisioning what happens, I got my beaker there, I've got some of the silver fluoride solid sitting on the bottom, and I've got these ions in solution. So if we look at the different modifications, so this first one, if I'm adding more silver ions, it's a common ion. I'm going to shift the equilibrium to the left, and I'm going to decrease the molar solubility. If I add more solid AgF, it's already a saturated solution. If I add more solid to it, that solid just sits at the bottom. I haven't changed the molar solubility at all. If I add some nitric acid, I'm viewing this as adding H+. I have a weak base there in the form of F-. So I'm seeing how those two could be combining and in a sense removing the HF from the beaker by adding H+ to it. In terms of the HCl, you could look at it in terms of the same thing of adding H+ that would react with the weak base. Or even more strikingly, you're going to have low solubility with silver chloride. Both of those would be acting in the same way of removing product from the beaker, increasing the molar solubility. Adding water, no change to the molar solubility. I think you could add water and have some of the solid dissolve, But that's not changing the molar solubility. The concentration of the ions is going to remain the same. We're not changing the molar solubility value. If we were to go through and solve for x, we would still have the same x value. So we got to be a little careful here. There's a difference between saying you would have more of the solid go into solution versus that you would change the molar solubility. If I'm adding ammonia, I could have a complex form. That's another way to remove a product from the beaker, increase the molar solubility. Heating the solution, I might need more information on that because some of my dissolutions are exothermic and some are endothermic. My hunch is that this one's probably exothermic, but it's only my hunch. I need more information on that. I need to know how does changing the temperature change this K value. Balancing a redox reaction under acidic conditions and identifying the reducing agent. Here's a representative response, a very strong one, where we're seeing all the details given with the whole process working through. I thought people did an outstanding job on this question. Another one involving electrochemistry. This is an electrochemical cell where what's being described is the standard hydrogen electrode. A platinum electrode immersed in a solution where the concentration is 1 molar H plus and a partial pressure of H2 in that chamber is at 1 bar. When this is connected and operating, it says that the solution near this electrode becomes more acidic. How do we make sense of what's going on? Key thing is, as this is operating, there's a redox reaction taking place at that electrode, and we have the solution becoming more acidic. As shown in this work, when it comes to the standard hydrogen electrode, we can either have a reduction take place or an oxidation. It depends what it's paired with as far as what the spontaneous reaction then that occurs. So this one, H plus is being produced, becoming more acidic because the oxidation is taking place. The H2 is being oxidized and becoming H plus in that chamber. So my standard hydrogen electrode is acting as the anode. If it's paired up with something where this is occurring, the other one must be acting as the cathode. The reduction must be taking place there. And this is how we could then place it as being higher on our standard hydrogen standard reduction potential scale. Must be a positive value compared to the standard hydrogen electrode, which is defined as a value of 0 volts. Using standard reduction potential data to determine a KSP value. Key thing within here, we need to combine the reactions in order to have it result in what the KSP value is. We need to have the AgCN as a reactant and have our product be the corresponding ions, Ag plus and Cn minus. So that tells me that I must be taking this first one here and designating it as the anode. I can't have a reduction take place. I need an oxidation to take place in order to get the silver ions. And this other one here, that must be the cathode. I must have, starting with the AgCN, having a reduction take place, and that's what leads to the Cn minus anions. We could see if we were to combine both of those and have them cancel as we add them together, it would result in the overall reaction we're looking for. The key thing that I saw with this, as far as folks having trouble, they set it up to be a spontaneous reaction. We're not saying it's a spontaneous reaction. We're saying we can use the standard reduction potential data and come up with something that has a very small, and in fact negative, standard reduction potential. It doesn't reach our values of ones all the way across. It's going to give me a KSP value that is a very, very small value. So as we work this through, I saw people set this up 2 different ways. This would be an example where they took both of the cells. They had a cathode and anode. In both cases, they used the standard reduction data to come up with what a K value would be. And then those were combined to come up with what the KSP expression would be. This was an interesting way to do it. It works. It wasn't what occurred to me. My strategy would be more consistent with this one, where I would be combining my cathode and my anode as I've just defined them and I find that I end up with a negative voltage. It's negative voltage because it's not going to reach my standard values. It's going to give me a value that's really small, which is appropriate here. So this would be another way of taking the cell potential and using it to convert it to get a K value. A comparison here of an electrolysis experiment, if it's a molten ionic compound versus in water. This was a pretty complete explanation. This is the most complete explanation I saw, where there was a description of what was going to take place in the molten scenario and how if you had it aqueous, how the water could interfere, especially the water being more preferentially reduced compared to a cation like sodium plus. And there's also a discussion about oxidizing of the water compared to the competing anion that would be present. Looking at the notation that we have for a cell and some provided standard reduction potential data, being asked to then make a sketch of the cell and analyze it in different ways. A lot of people had, I thought, high quality sketches, adding plenty of details for how it was set up. This is the one that we see time and again where we have a zinc electrode and a copper electrode. The idea here is that as this operates, the E naught for the cell isn't changing, but the measured E cell that you would have would decrease over time as you're changing the amount of the reactants and products present. And by reactants and products, I'm talking about what's in the ions in each of our chambers here, within the anode and the cathode. This last part of what would happen if we added some water to this chamber holding the zinc electrode. There were really two different competing answers here. Some folks, it seemed like, were thinking back to the question that we just had about how water could compete in an electrolysis experiment. And so there was descriptions here about how that would be taking place, how it could be in competition with that. The best answer within this one would be how it would be changing the concentration of the zinc ions. By changing the concentration of the zinc, we're changing the Q. If we look within our Nernst expression there, that leads to a change in the measured voltage, and it makes it more positive. So I thought most folks had a strong consensus on what was taking place for the top part of this question, and more of the variability was what would happen when we added water to that particular chamber. Last question here was looking at electrochemical cells, thinking about maybe electrolysis, plating experiments, a battery, ion selective electrodes. Most of the responses were involving the electrolysis plating experiment, and most were quite comparable in terms of how comprehensive they were. One feature that I would say some people omitted within that is the plating part. There was a discussion of what electrolysis might be, but not what the plating feature there is. So this would be a plating experiment where what's being plated would be like this fork. So it's being silver plated. The whole point of doing the electrolysis experiment was to put a coating of those ions that would then coat the surface, and maybe you're using chromium, maybe you're using silver, maybe you're using nickel, but you've got a different object that's serving as your electrode, and you're plating it, covering it by applying a power source and having those ions then turn into the solid that's covering it. Wanted to share this one about the battery. This was probably the most comprehensive for this question for any of the aspects that people chose to respond to. So this was quite a complete description of what was taking place with the lithium-ion battery. Just sharing it with you because I was impressed with the level of detail, and you might be too. That's all I got for you. Thanks for your time.